Hello viewers of mine, this is a What the Physics video. This one is on planetary universal gravitation, as in universal gravitation, but on the planetary scale. So we're going to be dealing with some large numbers for mass, and finally, we're going to have some large numbers for forces, as opposed to the gravitational force between you and a pencil sitting next to you, relatively small. So here we are. Ganymede orbits 1,071 times 10 to the 3 kilometers, notice in italics kilometers, from Jupiter with a period of 7.155 days. Callisto orbits Jupiter every 16.69 days and has an orbital radius of 1,884 times 10 to the 3 kilometers. Now, before we even start looking at the questions, I do need to point out, as we said, kilometers. We should be in meters, so we'll need to convert that. This was how the resource that I had presented it. They, for some reason, were always presenting in kilometers. So that's an easy conversion. Days, that's an easy enough conversion as well. But I do want to point out that when we're saying it orbits, we're talking about the moons going around Jupiter. So let's see, if we've got Jupiter right here, and these are some of the moons going around Jupiter. So like this is Ganymede, for example. When we're talking about this, of course, that's going to be some circular motion. That radius there is going from here to here, from the center of one object to the center of the other object. That is the orbital radius. That is not what we'd call the planetary or lunar radius. Okay, if we take a peek at these values right down here, and I even wrote them out for us to make it easy, yeah, that number of kilometers would be very, very sizable. If we're talking that is the size of the radius of the moon or the planet. There's no way that's happening, at least not in our solar system. Okay, so what is the gravitational force between Jupiter, whose mass is this, and Ganymede, whose mass is that? And then part B, what is the gravitational force between Jupiter and Callisto? Callisto has this mass. Okay, so as I mentioned, we have this listing here. Ganymede, radius, already mentioned, this is still in kilometers. The period, which is in days, and then the mass, which is in kilograms. Likewise for Callisto and Jupiter, we have the mass for Jupiter. Okay, so we would want to go ahead and convert this from kilometers into meters. So that's shifting it over 3. Also notice that this is 1,071. So that's another 3 spaces we're going to have to move it over. So I already did the conversions because I'm so awesome. I love this stuff. So I'm just going to pop it right up here. Okay. All right, so those are the R values, or you can say the D value that we would use for Newton's law of universal gravity. So you do want to make sure that your units are, of course, correct. Speaking of units, oh man, what do we have to do with days? Do we have to convert days into seconds or something like that? Well, seconds is the standard unit for this, but if we think about the equation for universal gravitation, because we are looking for the force between these two objects, we have their masses and we have the distance between them. Do we even need the period? No, we don't. So the period is just a distraction. Now, could this be useful for some other scenario? Absolutely, absolutely. But we don't need it for this problem. Okay, so here's my equation. It's universal gravitation equation. Force between Jupiter and Ganymede. That's what I set it up as, J-G. That G there is Ganymede. That is not to be confused with this G right here. And I'll use my pen to emphasize. This G right here is the universal gravitation constant. The subscript G here and here, that is going to be standing for Ganymede. Okay, and then of course don't forget to square the distance between them. That is one of the most common mistakes. So I'm going to go ahead and write out the information. Here we are. Look at how fast I wrote that out. No, it takes a while. That's why I wanted to pre-write it out for us. Okay, and then we want to punch that into our calculator. Tap, 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 tap. And we have the force between Ganymede and Jupiter is 1.635 times 10 to the, so we're using small size capital E, 22 newtons. So now we're finally talking about some really sizable forces here. I'm going to round this a little bit. I'm just gonna, you'll see why it's important to do this later on. 1.6 E 22 newtons. Okay, then we're going to do the exact same thing for Callisto and Jupiter. So we're going to use the R value for Callisto, but this one in green because it's in meters. We don't care about the period for Callisto. We're going to use Callisto's mass, Jupiter's mass, and the distance in between them. We're going to square that. So here's our equation for Jupiter to Callisto, and then we do some mathin'. So there we are, and we're going to tap that into the calculator as well. And we have a delicious value for the force right here. That is going to be 3.856 E 21 newtons, or approximately 3.9 E 21 newtons. Okay, so that's that. That's the solving. This was a pretty straightforward, just straight up calculation thing. But of course, I did want to follow it up with a comparison. I specifically chose these moons on purpose. I went through like all these different planetary objects, and I found ones that work nicely. By the way, little side note, these are 2 of the 4 Galilean moons, Ganymede and Callisto. Ganymede is the largest moon in our solar system, larger than our moon. Earth's moon is called Luna, by the way. It's actually, Ganymede is larger than Mercury. So that's something pretty surprising. So yeah, if Ganymede were orbiting the sun all by itself in its own orbital path, nice just like us, it would probably be considered a planet. So it's neat to see how planets can have their own little, I wouldn't call them solar systems, but yeah, they've got their whole little thing going on. Okay, so Ganymede is nice and big, Callisto is nice and big. There's also Europa, which is really cool because that's got like some ice on it. And then the 4th Galilean moon, which I refer to as the dad joke moon, because it's Io, and I just, every time I tell a dad joke, I'm like, Io. So I'm thinking of Io. I've got the Galilean moon right there, right? Indeed. Oh yes, physics. Anyhow, these are important moons because these are the first objects that anyone had seen orbiting something that they had clearly seen orbiting something other than the Earth or the Sun. This helped to clarify that, yeah, things are not just orbiting around the Earth, like the originally considered geocentric model of the solar system. Okay, and they're called the Galilean moons because Galileo was the first person to see this. Galileo used the telescope. He did not invent the telescope. That was actually done many years before him, but he altered the telescope to use for astronomical purposes. Anyhow, yeah, so let's go ahead and see what's special about these. Why did I choose these particular ones? Well, first of all, these forces are quite sizable. These masses are quite sizable. They're not much smaller than the Earth's mass, right? And so the forces as we said, are going to be pretty large. But how when they're this large, it's like I don't even really know what that means. But what I do want to point out is I want to put these into values that are easier to deal with. So I'm going to rewrite this 1.6, and I'm going to change it into 16 E21 newtons. That's 16 times 10 to the 21 newtons. You say, well, why did I do it like that? Well, because this one in blue here for Callisto is 3.9 times 10 to the 21 newtons. We're going to get back to that. There's definitely a number ratio that I'm looking for here. So if we were to look at the values here, what I'm trying to do is compare the gravitational force between Jupiter and Ganymede and Jupiter and Callisto. Obviously, if we look at the big G is not going to change, nor is the mass of Jupiter. But if we look at the mass of Ganymede, 1.48 times 10 to the 23, and then the mass of Callisto, 1.08 times 10 to the 23. They're not twinsies, but they're really close. I mean, astronomically speaking. Obviously, one is considerably more massive, but astronomically speaking, yeah, they are really close. So I'm going to say they're close enough that they are twinsies for this comparison. And then let's look at the distances between Jupiter and Ganymede and Jupiter and Callisto. So Ganymede is 1.071, or essentially 1 This is essentially about 1 times 10 to the 9 meters. And then if we take a look at Callisto, this will take a little bit more rounding. Okay, this 1.884 times 10 to the 9. Oh, so about like 1.9. Yeah, I'm going to round it up a little bit more. I'm going to say that's approximately 2 times 10 to the 9 meters. Okay, once again, this is close enough. It's not like this is a simulation where I can just manipulate. I can pick up a moon and move it, or I can change the mass of the moon. But as you can see, Callisto's distance away from Jupiter is about twice that of Ganymede's distance. Okay, so close enough. Callisto is about twice as far away. Now, if we look at the force between Jupiter and Ganymede, and then the force between Jupiter and Callisto, how do they compare? And this is why I changed the exponent here, so it's more obvious. 16 times 10 to the 21 and 3.9 times 10 to the 21. Not perfect, but this is essentially a factor of 4 difference. So when we doubled the distance here, this is now a quarter of the force. And that is what we're seeing if we were to just go back and look at this equation here. This is just the generic force. Let's see, put in the spacers here. Okay, big G, which is not going to change. I'll just say mass 1, mass 2, and then R, and we're going to square that. And if I were to keep these masses approximately the same, because, well, the big mass was the same, but the little masses are close enough. If I were to double the radial distance, the distance between the two planetary or the two large objects here, then I would have a 2 down here. Remember that 2 would get squared, so that's going to be 2 squared, 1 over 2 squared. It would be 1/4 of the force. That's exactly what we see. So it took a while for me to actually find 2 large objects that worked out this nicely, and that their masses were pretty much the same. But yeah, that's really cool. I think that's a great example of physics.